Our world is full of radio signals, and when I'm moving around, when I'm walking around, I influence the propagation properties of these radio waves. So the reception, the strength of radio signals depends on where I stand. Kashan Alidjan, that's exactly the topic of your research.
Exactly.
Because the radio networks basically create one big sensor network, and we can use that.
Correct. The advantages of the already often present channels can be used to understand the exact changes in the environment, and we don't necessarily need extra hardware to do whatever localization that we want.
So even if there are no sensors around, the simple fact that there are radio links all around us can measure me.
Exactly.
So when I'm walking around, basically the interesting question of your research is, what does my body do to these radio waves? Does it reflect it? Or am I just one big absorber of the energy of the radio waves?
Exactly. And can that information tell us something about where we stand in the room?
Or about me?
Or about you?
Interesting. So my first guess would be I'm just equivalent to a bag of water.
Exactly. One might think that, especially since we consist of about 70% of water. However, truth be told that we are slightly different from water. So maybe it's an interesting idea to first look at how water reacts.
How water reacts. So this is not me, this is water.
This is a sphere of water. So we have a ball that we fill up with water, we do a measurement and we check in with a model how the water responds. And as you can see, from the larger spheres of water we have larger absorption, and then for the smaller spheres we have smaller absorption.
So this is the amount of absorption for a certain sphere of water.
Yes.
And that's a smooth line.
Yes, the model is a smooth line. And then we see in the measurement there may be some noises involved. And what's most important is that we see on the lower frequencies that there are some resonances, especially for the smaller spheres we see more resonances up to about 1.5 gigahertz. And then for the larger spheres we have less resonance. And this is due to the integer wavelengths that fit in the sphere as we do a measurement.
So that sounds like I'm not exactly a sphere.
Not exactly.
So maybe this is not exactly the correct model, or you may know better.
If we compare this to, for instance, a human measurement, then we see that a sphere cannot represent a human. So this is all these lines that you see here are the spheres of water, of demi water that we have modeled. And if we use the measurement of a human in yellow, then we see that it doesn't fit perfectly.
Sounds like a big relief.
Yes.
There's a difference between me and a bag of water.
Yes, you are more than a bag of water. And how more is exactly how it's described in this curve.
So it looks like at the lower frequencies, around 1 or maybe even 2 gigahertz, I would be a big absorber. But at the higher frequencies, that model goes broke. It does not really represent how I would influence, or how you would influence the radio waves.
Exactly. On the lower frequencies we see that the absorption changes significantly over a small portion of frequency. Where, however, if we look at the larger frequency, also in smaller bands, we see that we follow the curve of water, and this is highly due to the fact that we have so much water in our bodies. But it's imperative to note, indeed, there is differences in regions.
Okay. And then it's interesting, why do you want to know this? We will come to that, because it helps to monitor the environment, to monitor what we do in that environment.
Exactly.
But first, I guess you would like to have a better model of us as absorbents.
Exactly. If we look at different people and different measurements that we get, is that we see that one person differs significantly from the other person. However, most important to note is that on the lower frequencies it seems to be some form of a scalar or some of a multiplication by a single number, and then on the higher frequencies you see that two people seem to overlap slightly.
So some people are more equivalent on the lower frequencies and other at the higher frequencies. Do we already understand why that is and how that comes? Or
yes.
Is it just...
One of the reasons that, for instance, the purple curve is completely different from the other curves is that that person was a lot smaller respectively to the other people. And the other thing is that on higher frequencies, the water takes over, so to say. As we saw in the previous plot, we see that the slope of the curve is rather equivalent to the slopes of water.
So can these radio systems then determine who is in the room?
Perhaps. That's what my research is about. So if we look at different time instances, we see that there's some variation per person over different plots.
So this is The same person.
The same person over different moments.
Okay.
And there seems to be some
Looks
moments,
like it's almost the same, except the day that I had a hangover.
perhaps, or perhaps it was a hot day, you sweated a little bit more, or maybe you didn't drink enough water, because this was the main key impacting parameter in that measurement.
So by monitoring the radio environment, I can see whether you are sick or feel happy or...
Potentially, yes. Bodily functions are heavily impacted, as we can see in the plot. However, this should be taken as an average, and then we see that it's quite tough to specifically say how someone is responding. This is more so comparing it to a different plot.
And this spread here, for one person, may also be the same spread as the spread between two persons.
That could potentially be. If the parameter sets that we find from our model are quite similar for two different people, then it's almost impossible to distinguish, do we have person A or person B in that room?
Okay, so now we know how the radio environment changes when people move around. We even see differences between people. What was exactly the purpose of your research? Why were you doing this? To monitor people? To see what I ate the other day? Or?
Yes, no, the true purpose was not to monitor any person individually.
Yeah.
The goal is to see, can we optimize our usage of energy? Let's say someone is in an environment, that's what the project LoLipop is about. Someone is in an office environment and half of the office environment is not being used. Then there doesn't need to be any light, any energy, any heating, any air conditioning. Though this may affect people in a different way, that's the other side of LoLipop. The important part in my research is, can I identify where people are so that I can reduce the energy waste? And this is especially interesting for situations where emergency services need to know if there's people present in an environment, or for security to know if there has been a breach.
Yeah. Or indeed to know when you switch off the lamps or when you open the window to get more fresh air in.
Exactly.
An interesting name. You call that project, the whole team calls that project LoLipop-IoT.
Yes.
It's a fun project, I guess.
Yes, it stands for Long Life, Power and Platforms in
Yeah.
Internet of Things. So anything to do with smart environments, Internet of Things environments, where we can improve the power efficiency and energy efficiency.
Yeah. So on one hand, that could mean that we shrink the power consumption of the devices itself, make more effective sensors. Or we could say, well, we already have those sensors, we use the existing radio connections, and then we save a lot of energy by using that information in a smart way.
Exactly, especially in indoor environments where we have multipath components from reflections of the walls and of the ground and any other surface in the room. It becomes incredibly useful to measure out the channel and then know where the human is based on already present channels. So indeed, the focus is on using the network that we have rather than reducing the energy that we put in.
You did measurements on real humans, you analyze it, you create models. A next step in your research is to use this indeed to characterize where the human is. Because isn't it that the only thing you need to know is whether the human stands in front of the line of sight and blocks that radio waves?
Yes.
So then you know whether you're in that virtual line between the transmitter and the receiver.
Indeed, the line of sight is the strongest component in a radio channel. However, for any other line of sight or non-line of sight component, any reflection of the wall, it is already being measured in the channel. And therefore, if I can already say before I stand in the line of sight, if I already know where I am in the room, that gives me much more insight on what is happening in the environment.
So then the idea is that there are so many reflected waves, and if you're in the path of a reflection, you may also measure that.
Yes, I may also measure that, especially because I know exactly how well I absorb on what frequencies.
And that's exactly where the math comes in and where the signal processing comes in. You want to know it at all these frequencies, because then you can resolve which reflections are actually influenced.
Exactly.
By translating frequencies and responses in frequency domain to positions.
Correct. That's the purpose of this research.
You like to do the hard math rather than to throw in artificial intelligence and just do something with a lot of data.
Indeed, using classical equations for physics and geometry, we can find these solutions way easier than applying a complex model or a complex AI algorithm before we even did the preliminary work.
You can find them more quickly. You can also imagine that the training of this whole network can now be a very specific training, because you know exactly
Yes.
that you want to find where the reflections are from a couple of frequency responses.
Indeed, the physics that I already have used to describe this can now be implemented potentially in a model, in a machine learning environment, to optimize even quicker what the solutions would be on where people are in the room.
Kashan, I guess some people may like to follow what you're doing, may like to read papers where you already presented and published the work.
Indeed, the research that I've shown you so far, that's been published in IEEE EMC Europe last week. It was a successful conference. We had quite some people attending, and all of the maths and all the physics is explained in this paper.
IEEE EMC Europe 2025, and search for the author Kashan Alidjan. Thank you very much.
Thank you very much.